Question number 2. So a key idea in question number 2 is that in general, if we want to find f of x values using an integral or using area, we need some starting value. So up here I've got f of a as our starting value, and we need the displacement on f to get the y coordinate. So we have a starting y coordinate, we get a change in y, and that change in y is going to be based on the area, okay, that function there, the area function. Okay, so in general, that's how we're going to set this up. Question number 2 says, a particle P is moving along the x-axis. The velocity of particle P at time t is given by Vp of t is equal to sine of t to the 1.5 from the time interval 0 to pi. In its starting position, at the time t equals 0, the particle is at position x equals 5. Okay, so that's our position. That's where our starting position that we're going to use. And we're talking about the x coordinate, so that's why it's in terms of x. A second particle q moves along the x-axis, and the velocity of particle q is given by the function vq of t is t minus 1.8 times 1.25 to the power of t in the same time interval. And for q, the starting point, t equals 0, is going to be at x equals 10. Okay, so that's important. We have starting points. We have the velocity function, which is the derivative, and we're going to find the area underneath that derivative to find the change in the positioning. So for part A, for P, I'm going to do this in red. We know that we can say x of t, so the position of t of P, position of particle P, is going to be equal to the starting point. So in this case, the starting position is going to be x at 0. So that's going to be equal to 5 plus the displacement from that point. So that point was starting at t equals 0, so that needs to be the same. Okay, just like I have here in my formula, that f of a and a have to match. And then we're going to end at some time t. So I'm just going to generalize it for now. And that's going to be underneath the velocity function. I'm going to change that to x just so that it doesn't conflict with a t variable. Okay, so there's my positioning of the v of p. Okay, or the position of particle p. Okay, and then we're going to do the same for particle q. We know that particle q, the x position as a function of time, is going to be equal to, now we need a starting point for particle q. In this case, the starting point is going to be x is 10 when t is 0, so I'm going to start at 10. And then I'm going to add the change, and that change is going to be calculated from t equals 0 to whatever t we want. Okay, and that's going to be, the displacement is going to be the area under the velocity of q. And again, I'm just going to change that to x so that it doesn't conflict with the t that we have in our integral. Okay, so those two expressions then represent the positioning of p and the positioning of q. Now we want to find this for t equals 1. So I'm going to do this for x of p at 1 is equal to the starting position of 5 plus the area under the curve from 0 to, now we want to do from 0 to 1. So that area that we're going to find is going to be this area here. So I've drawn in here. The first thing we're going to do is we're going to make sure we have these graphs drawn. Okay, and we have the area under the curve from 0 to 1 is going to be represented by that area there. That's what I want. That's going to be the integral from 0 to 1 of v of p. Okay, so that's going to be, I'm going to work that out. So the position at t equals 1 is going to be equal to the starting position of 5 plus now the area. So I go to my calculator I'm going to use that calculate the integral function on the calculator, and doing so, we should get an area of 0.37, looks like 37066, so I'm going to round that to 0.371. Okay, so that's going to be the displacement. So I'm going to go forwards 0.371. I'm going to start at 5. So my position at t equals 1 is going to be 5.371 in the positive direction. Okay, so that represents the position of particle P. So then I could do the same for particle Q. For particle Q, I start at 10, and that displacement is going to be from 0 to 1. So I'm going to write that in. So x of Q at t equals 1 is going to be starting at 10. And then I'm going to add the displacement from that starting time of 0 to 1 second. And that's the area underneath the velocity function v of q. So that area, so at t equals 1 is there. So that area is going to be here, because this is going to, it looks like it's negative velocity for that whole period. So I'm going to have negative displacement. Okay, so I'm going to, again, go to my graphing calculator. I'm going to graph this. I'm going to use the integral function to integrate and find that area. And that area works out to be negative 1.436. It looks 356, so I'm going to round that to 6. So working that out then, I get x of q at 1 is going to be equal to 10 plus the area. That area works out to be negative 1.4, so that displacement, I went to the left, 1.4356, so I'm going to round that to 6. Okay, and then that means that the position of particle Q at t equals 1 works out to be 8.564. Okay, so that's going to be 8.564 meters to the right. For part B, it says the particles P and Q are moving towards each other, or are the particles P and Q moving towards each other or away from each other at time equals 1? So what we need to do then is we need to figure out at time equals 1, okay, so the position is going to be 5.371 and 8.564. So that's the positioning. So maybe I'll just make sure that's clear. This is going to be the x positioning at t equals 1. We want to know the v at that same time. Okay, so v of 1. And for the p function in the red, we can just take a look at the velocity or the y coordinate of that velocity. So I can just calculate the value. So the calc value of x equals 1 is going to give me positive 0.8415. So that's going to the right. Okay, so in this case here, that function is going to be, the velocity is going to be going in this direction. Oh, the velocity is going to be going in this direction, positive 0.8415. So I'm going to round that to 842. And then we take a look at the particle Q, and we look at the velocity. And the velocity, we want to see which direction the velocity is. So we could compare the directions, and then we can see if the particles are moving either towards each other or away from each other. So looking at particle Q, we can take a look at the velocity. So we're going to look at the velocity function and calculate the velocity when t equals 1. So this is the y coordinate of that velocity function. That velocity we can see from the graph works out to be -1. So at that time, there's particle Q. It's going to be in that position, and it's going to be moving in this direction. Okay, so it's going to be -1 is going to be the velocity. So by looking at the diagram and their positions, you can see that their relative position, because Q is to the right, okay, in red, so this is going to, or sorry, in blue, that's Q. P is to the left in red. We can see that because their relative position and the direction of their velocities, they're moving towards each other. So using that diagram, we can explain or show our reasoning behind this and just state that they are moving towards each other.